So my plan is to try to give an introduction to the combinatorial theory of the rigidity of frameworks. So my original plan was to kind of do a survey talk of lots of different frameworks. But while I was preparing these 3 lectures, I decided it would be better just to concentrate on bar joint frameworks in D-dimensional Euclidean space. So I think these are in some sense the simplest, and yet at the same time the most intriguing kind of framework. And I think they reflect most of they give a good introduction to most of the ideas we need for a theory. So that's what I'll do. And today's lecture, which is the first lecture, will introduce basic concepts and notation for bar joint frameworks in D-dimensional space. And then I will towards the end of the lecture, I will focus on 2-dimensional space and present some important results and proof techniques for this 2-dimensional case. And then I decided that I would use the second and third lectures to address the important unsolved problem of generic rigidity in 3-dimensional Euclidean space of bar joint frameworks. So this was mentioned by Mira as a fundamental problem earlier on today. And so I'd like to give an indication of what's known and what is conjectured to be true about this 3-dimensional case. So before I start, so Tony is chairing this session, and he's kindly agreed to keep an eye on the chat. So I can't see the chat. So Tony, if somebody has a question, then they can put it on the chat, and Tony will either answer it directly or he will interrupt me and tell me to answer it. I hope that's okay. So to start off with the basic definitions, or a D-dimensional framework, bar joint framework, is a pair. And it's a pair where the first thing in the pair is a graph, and the second thing is a map, which maps the vertices into D-dimensional Euclidean space. And we think of this as a realization of the graph in D-dimensional Euclidean space. So the map gives us the location of the vertices, and we think of the edges as being straight line segments joining the end vertices. The length of an edge is given by the Euclidean distance between the 2 end vertices. So the framework is said to be rigid if every continuous motion of the vertices, which preserves the lengths of the edges, actually preserves the distances between all pairs of vertices. So this is equivalent to saying that every continuous motion, or the result of every continuous motion, can be obtained by a rigid motion of D-dimensional Euclidean space, isometry. So here's an example. So the first 2 frameworks on the left are examples of 2-dimensional frameworks which are not rigid. So the rectangle, we can continuously move the vertices into the parallelogram, keeping the lengths of all of the edges. But it's not a rigid motion because it changes the distance between the vertex V2 and V4. The framework on the right is rigid, and in fact it's what we obtain from the framework on the left by adding an extra edge or a brace, which kills the motion into the parallelogram. So just to finish this example, it's worth noting that the framework on the right is a rigid framework in 2-dimensional space, But if we imagine that we're in this, the framework was actually in three-dimensional space, and the vertices just happened to lie in a plane in three-dimensional space, then it would not be rigid. So it's not rigid because we can rotate the vertex V2 about the line through V1 and V3. And that will preserve the lengths of all of the edges, but it will change the distance between V2 and V4. So I guess rigidity depends on which dimension we're working in. Oh, that's strange. Sorry. I got distracted because well, I can't see the title of the slide because I've got the Zoom stuff in front, but never mind. So this is about algorithmic complexity of frameworks. So I think another thing that Mira said this morning is the people working in the area are very interested in whether their results can be turned into efficient algorithms for deciding rigidity or flexibility. And this is a negative slide in that sense. So if we have a one-dimensional framework, so the framework is on the line, then it's very easy to decide whether it's rigid or not. So it's rigid or not, if and only if the graph is connected. So the idea is if the graph is not connected, then we can choose a component of the graph and it can move freely along the line without changing the length of the edges, but it will change the distance between a vertex in this connected component and any of the vertices in any of the other connected components. So in order to be rigid in one dimension, the graph needs to be connected, rigid in any dimension. And you can also show it's sufficient, and that one way of doing that will be to use an easy induction. So if the graph's connected, it has a spanning tree, and you could use induction on the number of n vertices. Sorry, on an n vertex of the spanning tree. So use induction on the number of vertices. So the negative result is due to Abbott in 2008 in his MSc thesis, and he showed that for any d greater or equal to 2, it's NP hard to determine whether a given framework is rigid. So there aren't going to be any efficient algorithms which will work for an arbitrary framework. So that tells us we have to concentrate on particular frameworks, and one particular family that the combinatorial theory is particularly appropriate to is the idea of generic frameworks. So the NP hardness for a general framework seems to depend on algebraic dependencies between the coordinates of the vertices. So one way to get around this is to restrict our attention to generic frameworks in which the set of all coordinates of the vertices is algebraically independent of the rationals. So we'll see in a few slides' time that if we restrict to generic frameworks, then the actual realization P doesn't matter as long as it's generic. So deciding or not whether a generic framework GP is rigid or not just depends on the graph G. So this gives us an algorithmic problem of determining which graphs are generically rigid in d-dimensional Euclidean space. And as we saw in the first bullet point, this is easy for d equals 1. In fact, it can be solved for arbitrary frameworks, not just generic frameworks. And it was also solved, it can also be solved algorithmically for d equals 2 using a theoretical result of Polacek-Geringer, which again, we will see towards the end of the lecture. So that's d equals 1 and d equals 2. As soon as we get to d equals greater or equal to 3, it becomes an an important open problem whether the graph is rigid or not, generically. It would be nice to see what the title of my slides were. So the rigidity of, maybe if I go out of, sorry. So, is that better, Tony? Are you there, Tony?
You've come out of full screen, so it's worse for us, but if it's better for you, it's readable. I think it's big enough.
But could you say the title of the slides before?
We could see it, yes.
Oh, all right. So, so I won't worry about it then, should I not?
Yeah.
Okay. So I think this is about the I think this is about the rigidity matrix. Oh, it's confusing me now. I think I really need to know what the title is. Sorry. So the sorry. So we can the decision problem of deciding whether a particular framework is rigid or not is related to determining the solution space of a system of quadratic equations. So the idea is that we imagine that the vertices are moving around in d-dimensional Euclidean space, and that the position of a particular vertex at time t is given by pt of v. So p0 of v would be the initial time, which is, so p is equal to p0. And so the constraint that the length of the edges should not change as the vertices move can be formulated as this system of quadratic equations, where we have one equation for each edge. We can simplify this system by, well, we can linearize the system by thinking of the motion as being a smooth motion and differentiating with respect to time t, and then putting t equal to 0. So if we do this, then at time 0, the instantaneous velocity of each vertex is given by p dot u, and the system of quadratic equations 1 is transformed into the system of linear equations 2. And linear equations are much easier to solve than quadratic equations. So solve a linear system, we look at the matrix of coefficients, and we call the matrix of coefficients of this system the rigidity matrix. So because we've got the number of equations is equal to the number of edges, the matrix of coefficients will have the number of rows will be the number of edges, and the number of columns will be the number of variables. And the number of variables is just the so the unknowns are the instantaneous velocities p dot, and each vertex has its instantaneous velocity has d coordinates. So we get d times v columns corresponding to the d times v unknown coordinates of the instantaneous velocities of the vertices. And the entries in the rigidity matrix. So the coefficient of P dot U will be P of U minus P of V, and the coefficient of P dot V will be P of V minus P of U, and the other coordinates in the row corresponding to the edge UV will be 0. So it's an E by dV matrix, and its entries are given by these rows. So for example, if we go back to our square framework, then this is the corresponding rigidity matrix. And if we're interested in the number of solutions to this linear system of equations, then we're interested in the rank of this matrix. And the rank, well, it depends on where the vertices are placed. So if, assuming that none of the vertices are on top of each other, so these are on the P of Vi minus P of Vj entries are all non-zero, then the rank of this matrix will be 3 if all 4 vertices are coplanar. Oh, if all 4 vertices are collinear, sorry, and otherwise it will be 4. So this tells us that the generic rank of this matrix, if we imagine that the points are spaced generically in d-dimensional space, then if d is 1, the rank will be 3, and if d is greater or equal to 2, the rank will be 4, and the rows will be linearly independent. So an infinitesimal motion of a particular bar joint framework is the vector p dot we get by concatenating all the instantaneous velocities. So it's this is a vector in the null space, or the kernel of the rigidity matrix. And fundamental observation of James Clerk Maxwell from 1864 was that each rigid motion of d-dimensional Euclidean space gives rise to an infinitesimal motion of the framework. And it's not difficult to say that the dimension of the space of motions, of infinitesimal motions coming from translations or rotations, will be at least d plus 1 choose 2, at least whenever the points span the whole space. If not, then we get some kind of degeneracy. So this tells us that the dimension of the null space, or the kernel of the rigidity matrix, will be at least d plus 1 choose 2. So using the rank nullity formula, it tells us that the rank of the rigidity matrix will be at most the number of columns minus this lower bound on the dimension of the kernel. And it tells us more than that. It tells us that if we actually have equality here, then every infinitesimal motion comes from a rigid motion of d-dimensional Euclidean space. So all of the infinitesimal motions are rigid motions, and it tells us that the framework will be rigid. So it's actually it's a sufficient condition for rigidity, but it's not equivalent. So depending on there are particular frameworks which can be rigid but are not infinitesimally rigid. So it's a stronger property, and we said that the framework is infinitesimally rigid if we have equality. So a kind of a result of Gluck, which probably gave rise to people working on generic rigidity, was that for generic frameworks, infinitesimal rigidity and rigidity are equivalent. So this is a kind of elementary result from differential geometry. So it means that if we're interested in the generic rigidity of graphs, then it's okay to take the linearization of the quadratic system of equations, and we won't lose anything. So it implies that for a generic framework, it's rigid if and only if either it's a small complete graph, which is this degenerate case when the vertices don't span the whole space, or if it has at least d plus 1 vertices, which because it's generic will span the whole space, then the rigidity matrix has rank what it is by Maxwell's observation. So it's d times the number of vertices minus d plus 1 just there. So this tells us, so this is the point that I made earlier, this tells us that for generic frameworks, the rigidity just depends on the graph, because for any generic realization, the entries in the rigidity matrix will be algebraically independent, so the rank of the rigidity matrix will be the same for all generic realizations. And another kind of algorithmic observation is that if we can determine, if we want to determine whether a graph is rigid in d-dimensional space, it's sufficient to determine for a particular generic realization whether the rows of the rigidity matrix are linearly independent or not. So the idea is that to determine the rank, we need to find a maximum number of linearly independent rows. And if we can construct a maximum set of linearly independent rows greedily. So if we know how to decide when a given set of rows is linearly independent, we can choose a row which we haven't considered yet and try to get a larger independent set. And if it does give us a larger independent set, then we grow the independent set. And if it doesn't, then we throw it away and we keep on going until we have a maximum independent set. So determining rigidity is equivalent to determining independence of the rows of the generic rigidity matrix. So that's nice, but it's a two-edged sword. So I guess we don't tell our students to use Gaussian elimination to determine the ranks of matrices, but this won't work for a generic matrix. If the entries are indeterminates, then the entries will blow Gaussian elimination.
Bill, sorry, there's a question in the chat. So Itamar, sorry, could you repeat the question? Because I'm not quite clear what motion you're referring to.
Well, I'm not too versed in what's going on, but the other day I asked about dynamics. I got some answer from Mira, but now that you mention explicitly motion, okay, the question is time plays any role here, or we are talking about something that I would call semi-static motion?
So I think I'm talking about a static motion. So an infinitesimal motion
okay.
is
okay,
static.
That's great. Thank you.
So a dynamic motion would be much more complicated.
Absolutely. Okay, thanks.
That's okay. It's nice to say that somebody's out there.
Yes. You know, there is static friction and dynamic friction. And if you move the framework, there could be implicit, hidden friction. But let's leave the physics out of it.
Yes, yes.
Thank you.
It's hard enough without it, I think. So there is already a well-established theory of combinatorial independence. And we can, so this is Matroid theory. And again, Mira mentioned this morning. So we can get a lot of, we can make a lot of progress by applying the results of Matroid theory to try to decide when rows of the rigidity matrix are independent or not. So here's a quick introduction to a matroid. So a matroid is a very elementary system which is based on linear independence in vector spaces. So it consists of a pair. Again, we have a pair, we have a ground set E, and then we have a family of subsets of E, which I'll call I, and we think of I as being the independent sets. And in order for the independent sets to give us a matroid, we need 3 axioms. So we want the empty set to be independent. We want any subset of an independent set to be independent. And then the third axiom, which really makes them work, is that if we have 2 independent sets and A and B, and the size of A is less than B, then we can find some element of B, which when we add it to A, we get a larger independent set. So this tells us that we can construct maximal independent sets greedily, and it also tells us that every maximal independent set will have the same size. So some more terminology. So as I said, the subsets of E which belong to I are called independent sets, and the subsets of E which don't belong to I are called dependent sets. A circuit is a minimal dependent set. So it's a dependent set for which all proper subsets are independent. We have the idea of a base of any subset of E. So given a subset A of E, then a base, sorry, this should say a base, it should not say a basis. A base of A is a maximal independent subset of A. And the third axiom tells us that all bases of A have the same size. And this size, this cardinality, allows us to define a rank function, which maps the subsets of A into the integers, non-negative integers. So the rank of any subset is the size of a maximum independent set of the subset. And so I'd like to apply this terminology to the whole matroid. So any base of the ground set A, I will also refer to as a base of the matroid M. And to the maximum size of a maximum independent subset of A, a base of A, I will also refer to that as the rank of M. And I'll denote it by R of M. So a classical example of a matroid comes from a matrix. So if we're given a matrix R, the row matroid of R, it's a matroid we get from the rows of the matrix, is the matroid in which the ground set is the set of rows of the matrix, and which any subset of rows is independent in the matroid if and only if it's a linearly independent set of vectors. So this immediately gives us a matroid corresponding to rigidity in D dimensions. So the D-dimensional rigidity matroid of a graph J is the row matroid of the rigidity matrix for any generic realization of the graph. And I'll say that the graph is RD independent. So the symbol I'm given for this matroid on the edge set of the graph J is Rd of J. And I'll say that the graph is Rd independent if its edge set is independent in its rigidity matrix. So this is the same as saying that the rows of the rigidity matrix are linearly independent. So we can use Maxwell's observation on the rank of the rigidity matrix to obtain a necessary condition for independence in the rigidity matrix. So given any subset X of vertices of the graph, we let I of X denote the number of edges of the graph which are induced by X. So the number of edges, both of those endpoints belong to X. And then Maxwell's observation tells us that if we have a graph, so this 2 should be a D. That's the problem with cutting and pasting. So if we have a graph, it's independent in the D-dimensional rigidity matrix. So the rows of its generic rigidity matrix are linearly independent. Then the number of edges induced by any set of at least D plus 1 vertices is at most D times the number of vertices minus D plus 1 choose 2. So the D plus 1 choose 2 comes from the rigid motions, D-dimensional Euclidean space. So it turns out that the Maxwell's condition is necessary condition for independence in the rigidity matrix is it's also sufficient when D equals 1, since it implies that the graph is a forest. So the one-dimensional rigidity matroid is well known in graph theory and matroid theory, and it's called the cycle matroid of a graph. So a set of edges is independent if and only if it's a forest. So Maxwell's condition is also sufficient when D equals 2. This is where the cutting and pasting went wrong. So now this 2 really is a 2. So Polachak-Geringer showed many years ago in 1927 that a graph is independent the generic 2-dimensional rigidity matroid if and only if it satisfies, if and only if each set of at least 2 vertices induces at most twice the number of vertices minus 3 edges. So independence in D equals 1 and D equals 2 is given by a sparsity condition on the graph. It's independent as long as no subset induces too many edges. And this famous theorem was actually known for a long time as Lahmann's theorem. So it was rediscovered by Lahmann in the 1970s, and then Brigitte-Savitius discovered that it had been originally proved by Polachak-Geringer many years earlier. So it does not, because this is a condition which works for all subsets of B, it's not immediately obvious that it will give us an efficient algorithm for testing independence or rigidity, but actually it does. So Jacobs and Hendrickson in 1997, they used this condition to give an efficient pebble game algorithm for testing whether a graph is generically rigid in 2 space. So unfortunately, or fortunately for us, things get more complicated in 3 space. So here's a famous example called the banana graph, which shows that Maxwell's necessary condition for 3-dimensional Euclidean space for independence does not give independence. So the three-dimensional condition is that any set of at least 3 vertices should induce at most 3 times the number of vertices minus 6 edges. And it's satisfied for this graph, but it does not imply independence. So this set of edges, set of constraints, is dependent. And to say it's dependent, we notice that the number of edges in this graph is 18, which is equal to the magic number of 3 times the number of vertices minus 6. So if it was independent, then this graph would be generically rigid in 3-dimensional Euclidean space. But it clearly isn't generically rigid, because if we look at the line going through V1 and V2, we can choose the right-hand component, right-hand part of the graph, and rotate it about this line, and it won't change the lengths of any of the edges, but it will change the distance between the vertices on the left-hand side and the vertices on the right-hand side.
Sorry, Bill, there's another question in the chat. I could answer this one, but I thought you'd like to know people are out there.
Yeah, sure.
But could you remind Alex of the notation IX and also RD independence?
So IX is the number of vertices. Sorry, so X is a set of vertices, and I of X is the number of edges induced by those vertices. So if I took X to be V1, V2, V3, V4, V5, then I of X would be the number of edges in this part of the graph, which is 9. And R3 independence would be, I would take a generic realization of this graph in 3 space. I would construct its 3-dimensional, its rigidity matroid for this generic realization. And then I would say that the graph is R3 independent if the rows of the rigidity matrix of this generic realization are linearly independent. Is that okay, Alex?
He said yes in the chat.
Ah, good. A closely related result is called the Henneberg construction for, I guess, the bases in the generic 2-dimensional rigidity matroid. So the idea is, rather than just thinking of a particular graph, we would like to think of all graphs. And one way of doing that is to think of all subgraphs of a large complete graph. So I imagine that, so Kn is a large complete graph, so n is large. And all the graphs that I'm interested in are going to be subsets, subgraphs of Kn. So it makes sense to look at the rigidity matroid R2 Kn. So the Policek-Geringer characterization of independence implies that the rigidity matrix, the rigidity matroid of a large complete graph is 2n minus 3. So this just comes from Maxwell's theorem, given that there exist rigid graphs. And that the bases of the rigidity matroid will be the edge sets of all minimally rigid spanning subgraphs of Kn. So these will be all the rigid graphs with n vertices and exactly 2n minus 3 edges. So I guess this is wrong. This is just Maxwell's observation. And the observation that Kn is generically rigid. So Polacek-Geringer comes into it because a proof is actually inductive, and it gives us a recursive construction for constructing all of the minimally rigid graphs, minimally rigid spanning subgraphs at the end. And it's based on graph operations, which were first suggested by Henneberg in 1911. So the first operation is called zero extension. So it's actually the two-dimensional version of zero extension. And here, this is a very simple observation. We just add a vertex of degree 2 to a graph and 2 new edges. The one extension operation, slightly more complicated. We delete an existing edge, E, and then add a vertex of degree 3. But when we add the vertex of degree 3, we have to make sure that we join the new vertex to both end vertices of the deleted edge. So you should notice that both these operations would preserve the condition that we have a graph with n vertices, that the number of vertices is, that the number of edges is twice the number of vertices minus 3. So the theorem that follows from Polacek-Geringer's proof is that the graph is minimally rigid in two-dimensional in 2D, if and only if it can be constructed from a triangle by recursively applying these two operations. Oh, I thought I had an example. That's right, I seem to have missed my example. Maybe it's going to come later, sorry. So I'd like to show you, sorry for jumping around so much. I'd like to show you why these two operations preserve independence in the two-dimensional rigidity matrix. So the first result is a bit more general. So I'd like, for reasons which become clear, I would like to state it as a result for an arbitrary framework, so not just generic frameworks. So the idea is that we have a graph G, which is obtained from another graph H by a zero extension, and we add a new vertex of degree 2 and 2 new edges from the new vertex to 2 existing vertices. And now we take an arbitrary realization of the graph, the large graph G, not necessarily generic, but we would like it to have the condition, we'd like to satisfy the condition that the position of the new vertex and the position of its two neighbors are not collinear. And we suppose also that if we restrict P to the smaller graph, then the rigidity matrix has independent rows. Then the conclusion is that the rigidity matrix of the larger framework has independent rows. And this follows easily by just looking at the rigidity matrix. So the rigidity matrix of the larger framework we get from the rigidity matrix of the smaller framework by adding 2 new rows. And this star will be, the entries in this star will be mostly 0, but underneath the column of W, there will be a P of W minus P of V. And underneath the column of X, there will be a P of X minus P of V. But the important point is that we have zeros here because these 2 columns correspond to the vertex V, and V only has 2 neighbors. So it's easy to see from the structure of this that, and the fact that P of V and P of W and P of X are not collinear, that these 2 vectors will be linearly independent, and hence, because this is linearly independent and this is 0, the rows of the larger matrix will be linearly independent. So RGP will have independent rows. And if we restrict ourselves to P, which is generic, then we will naturally have this condition that these vertices are not collinear. So it will tell us that the zero extension operation preserves independence in the generic rigidity matroid. So I'd like to show that the slightly more complicated operation of one extension preserves independence in the generic two-dimensional rigidity matroid. Again, we suppose H is independent, and the G is obtained from H by a one extension, which adds a vertex B, three new edges V, W, Vx, and Vy, and then deletes an existing edge XY. And I would like to show that if H is independent, then G is generically independent. So the construction is the two end graphs in the figure. So this is H, and this is G, and I get G by deleting the edge XY, adding the vertex V, and edges from V to X, V to Y, and V to W. So to prove this, we go through two intermediate frameworks. So the first thing we do is we add V on the line going through X and Y. And we join V to Y and W and keep the edge XY. Then this is a non-generic zero extension. So it's, if we're working in this framework, so we start with the generic realization P of H, and then we do a non-generic, we construct a non-generic framework P dash, in which V lies on the line between X and Y. But because we have a non-generic version of zero extension, V, Y, and W are not collinear because P is generic, and V is on the line through X and Y. So when we add V, we end up with this independent non-generic framework. And now we add the edge Vx, and we notice that a collinear triangle is a circuit. So the three rows in the rigidity matrix corresponding to Vx, Vy, and Xy are minimally dependent. So when we add the edge Vx, we have this minimally dependent set. And then we construct J by deleting the edge XY from the minimally dependent set. So I guess maybe it, oh, sorry, this hasn't turned out so so because the positions of X, Y, and V are collinear, we have a circuit in the row matroid of the rigidity matrix. So when we add the XY, when we add the edge XY, we do not increase the rank of the corresponding rigidity matrix. And then when we delete the edge, so if we start, sorry, I'm starting from the right. So we start off with the rigidity matrix of GP dash, and we do not change its rank if we add the edge XY, and we do not change its rank if after we add the edge XY, we delete the edge Vx because we have this minimum dependent set given by this triangle. So this tells us that the rank of GP dash is just the number of edges of the graph J. And so it tells us that the rows of the rigidity matrix of GP dash are linearly independent. And this The statement of the lemma is about a generic realization, and this is a non-generic realization. But if we have a non-generic realization which has linearly independent rows, then any generic realization will have linearly independent rows. So it tells us that generically we have preserved independence by the one extension operation. And this is the slide that I thought came earlier. So we can use the inverse of these operations to certify that a graph is minimally rigid or independent. So for example, if we start with K33 and we first use the inverse inverse of a one extension operation, which is a one reduction. So we delete this vertex and add an edge between two of its neighbors. And then we perform a zero reduction. So we take a vertex of degree 2 and delete it. And then we do another zero reduction. So we have a vertex of degree 2 and we delete it. Then we end up with a triangle. And it's easy to see that a triangle is minimally rigid, independent. And we also know that when we move from the right to the left by doing the zero extension and a zero extension and a one extension, we preserve independence. So that is this sequence of 4 graphs gives us a combinatorial certificate that K33 is independent. And because it's got 9 edges, this means it's minimally rigid. So to finish off with, I would like to give a slightly more complicated result of Lovasz-Yemini, which characterizes the rank function of the two-dimensional rigidity matroid. So there are direct derivations of this formula, but I think it's illustrative to use some machinery from Matroid theory to give you the Lovasz-Yemini formula. So in particular, it uses a classical result of Jack Edmonds from Matroid theory. So to state the result, which is maybe making it slightly more complicated than it has to be, we introduce the idea of a one thin cover. So we have a family of so we have a graph G, and we have a family of subsets of the vertices of J, and each subset has size at least 2, and each edge of G belongs to one of is induced by at least one of the subsets. This makes it a cover, and one thin means that any 2 subsets intersect in at most one vertex. So the Lovasz-Yemini formula from 1982 tells us that the rank of any set of edges in the two-dimensional rigidity matroid is given by the minimum of the sum of these numbers. And the minimum is taken over all one thin covers of the graph. Sorry, it's taken over all one thin covers of the subgraph of the graph induced by F. So the idea is that we have a set of vertices which induce all of the edges in F. And then for each vertex, we take twice the size of x minus 3, which is the maximum rank of any subset on this set of vertices. And then we sum that over all the sets in the cover. So here's an example of how we would use this. So we saw before that we could use the Henneberg construction to demonstrate that something is minimally rigid. So we can use the Lovasz-Yemini construction to demonstrate that something is not rigid. So it's clear that this graph is not rigid in 2 space because we can keep this complete graph on 4 vertices fixed, and then this will swing around on these two edges. So it's not going to be rigid, but to give a combinatorial certificate that it's not rigid, we cover the edges of this graph with 4 sets of vertices. So the first set, x1, is the left-hand plate, x2 is the right-hand plate, and x3 and x4 are the edges which join the two plates. Then the Lovasz-Yemini formula tells us that the rank of G in the two-dimensional, generic two-dimensional rigidity matroid is at most this sum, which turns out to be 12. So the rank is at most 12. So the maximum size of an independent set of constraints in this graph is 12. But to be rigid, it must have 13 independent constraints. It must have rank 13. So this is a combinatorial certificate that this graph is not rigid, generically. So to finish, I'd like to state Jack Edmonds' theorem. So a fundamental property of matroids is that the rank function is a submodular function. So more generally, a set function which maps the subsets of a set E into the integers is submodular. If for any two subsets A and B, f of A plus f of B is at least f of the union plus f of the intersection. And Jack Edmonds' theorem tells us that we can use submodular functions to produce matroids, and tells us what the rank function of these matroids are. So the idea is, well, we don't have just any submodular function. We have a function which is submodular and non-decreasing. So if A is contained in B, f of A is less than or equal to f of B. And I'd also like it to be non-negative on the subsets of E other than the empty set. So this idea of excluding the empty set is useful. So I'm going to get a matroid, and to tell you what the matroid is, I tell you what its independent sets are. So a set is independent if it's a subset of the ground set E, with the property that for all subsets J of I, the size of J is less than or equal to f of J. So then Jack shows that this is the independent sets of a matroid, and maybe it's more interestingly, he shows that subject to the condition that f of E is less than or equal to 1 for all elements of the ground set, it gives us a precise formula for what the rank function of this matroid. So the rank function is given by taking all partitions. The rank of a set F is given by taking all partitions of F and then summing this, the F value of the sets in the partition over all sets in the partition. So the condition that f of E should be less than or equal to 1 is not necessary. So we can remove this and get a slightly more complicated formula for the rank function. But for the application, current application to two-dimensional rigidity, we have this condition. So here's how we apply the formula. So we're interested in subgraphs of the complete graph on n vertices, and we define a set F. We define a function f mapping all subsets of A into the integers by putting f of any particular set of edges equal to twice the number of vertices incident with that set of edges minus 3.
Sorry, Bill, there's a couple of questions.
Mm-hmm.
Could you go back to the formula? I guess it means the previous slide.
Okay.
So I guess Will have had time to look at it. The other question is, are you willing to share the slides so that people can refer to them
Oh,
later?
for sure, yeah, yeah. So I'll send them to you.
Sure.
So is
I think
that
that's plenty of time.
okay? So we define our function f from the subsets of the edge set of our large complete graph by putting f of some subset of edges f equal to twice the number of vertices incident to f minus 3, which is the kind of magic Maxwell number. Then it's not so hard to show that this function f is submodular on E, on subsets of E, and it's non-decreasing, and it's non-negative on everything except the empty set. So this empty set condition is important because if f is the empty set, then this would be negative. That's 2 times 0 minus 3. So it's important that we allow it to be negative on the empty set. And now Polacek-Geringer's characterization of independence in the 2-dimensional rigidity matroid tells us that the 2-dimensional rigidity matroid is actually the matroid induced by this function f. So it tells us, Polacek-Geringer tells us exactly what it means for a set of edges or a subgraph of Kn to be independent. And it turns out that it's actually this. This is the condition for independence in the rigidity matroid. So the subgraph induced by F, the matroid induced by F is 2-dimensional rigidity matroid. And so Edmonds' theorem immediately gives this rank formula. And then to get Lovasz-Yemini, there is a small amount of work to do to show that if we take any partition of F which minimizes the right-hand side, and we can turn that into a one thin cover of the vertex set by letting the set of vertices in the one thin cover to be actually the sets of vertices which are incident with the edge sets in the partition of F. And then the last thing is just to show that any 2 of these vertex sets have at most 1 vertex in common, and that follows from the fact that we've chose something to minimize the right-hand side. You can show if it doesn't satisfy this condition, you can make the right-hand side smaller. Oof, so I've gone on too long, sorry. So I'd like to finish there.
Okay, thank you, Bill, for a really great talk. There was a question already in the chat. Does the minimizing partition have some intuitive interpretation or meaning?
Yes, that's a really good question. So if we, let's go back to the Lovasz-Yemini version. So if you imagine that you have a graph which is not rigid generically in 2 dimensions, then if it's not rigid, then you can look at its maximum rigid subgraphs. And the maximum rigid subgraphs give you a partition which minimizes the right-hand side. So if we take the vertex sets of the maximum rigid subgraphs, then this will give us one cover which minimizes the right-hand side. And the fact that it's one thin corresponds to the fact that if you take 2 rigid subgraphs which have 2 vertices in common, then their union will be rigid. So when we take the maximal rigid subgraphs, it's one thin. And in fact, that gives us the cover which has the fewest number of sets in it. So the other extreme, we can take, there is the notion of redundant rigidity. So a graph is redundantly rigid if when we delete any edge, it, I'm getting this wrong. Yeah, sorry. So a graph is redundantly rigid if when we delete any edge, it stays rigid. And the redundantly rigid, maximal redundantly rigid subgraphs will give us another cover, which minimizes the right-hand side. And it's a refinement of the cover that we get using the rigid subgraphs. Is that okay?
Yes, you got a thanks in reply for that. There are several more questions. So is this choice of the submodular function the only choice to obtain the rigidity matroid? Also, what if we picked a different function, i.e. not 2v minus 3?
So essentially, I think it is the only choice. So as I said, the rank function of a matroid is submodular. So we could choose our submodular function to be actually the rank function of the matroid, and rather than this simple version of the rank function. So if we chose f to be R2, then the matroid induced by R2 will be the two-dimensional rigidity matroid, clearly. But the advantage of this, taking this f, is that it's simpler than this formula. So the rank formula is quite complicated, but we can understand the matroid by a simpler submodular function. Is that okay?
I think so. Hank, you asked the question. Is that okay? Oh, he also asked about if you picked a different function. So I guess if you change the 2 and the 3, for example, it's okay. You just get different matroids.
Yes. So if you take any, you could take A times B of F minus B, and you would have, I guess, a submodular non-decreasing. Well, you'd want it to be non-negative on 2B minus the NB set. But yes, so that would give you a matroid, and some of the quite a lot of these matroids crop up in rigidity theory. So if you take twice the number of vertices of F minus 2, then it corresponds to rigidity on the cylinder. It's a bit more complicated than that, but if you have a framework embedded on the cylinder, then rather than having 3 rigid motions, you have 2 rigid motions corresponding to rotation and around the cylinder and translation up and down the cylinder. So the 2Bf minus 2 matroid is significant. It's more complicated because one thing you have to worry about is if you use the 2Bf minus 2 count, then it allows multiple edges. So you could take 2 parallel edges with the same end vertices, and they will satisfy this count. So we have 2 times 2 minus 2 is 4 minus 2, which is 2. And so you would allow 2 parallel edges, but clearly two identical constraints are not independent. So you have to add, you use the 2V minus 2 count, but then you have to add the extra constraint that if the number of vertices is only 2, then you do not have 2 parallel edges, and that makes things more complicated. So if instead we tried using the 3 times the number of vertices minus 6 count, which is what corresponds to 3-dimensional rigidity, then if we took just two vertices, that would tell us that 3v minus 3 times 2 minus 6 is 0. So if we just use the 3v minus 6 count, no edges would be independent. And so this makes the theory very difficult to apply, or more difficult to apply in 3 dimensions, because we don't only have to worry about the count being wrong for the empty set, but it's also wrong when the number of vertices is 2, and somehow we have to take account of that. I feel as though I've been rambling. Did that make any sense?
It did to me, at least. Lewis, do you want to ask your question?
Sure. So I had to go away. Sorry. So in this slide here, which is actually staring in front of us. So Edmonds' theorem tells you that you get a matroid out of this 2n minus 3, I guess.
Mm-hmm.
And is it true that, like, essentially Maxwell gives you then that this R2 function is an upper bound for the rank function for the rigidity matroid? Is that correct?
Yes.
Okay. So the main sentence here is that this MF is actually equal to the rank function, I guess needs a lower bound. Is that right?
Sorry, you said MF?
I mean, so I'm reading your slide. So you have R2, which is like your rigidity matroid, right?
Yeah.
Okay.
Oh, sorry, MF. Yeah. So the
and then
the
MF is your
F.
Edmonds matroid.
Yeah.
Right. Okay. So the equality. So I guess at what point do you use Polacek-Geringer, right? Maybe that's the.
So Edmonds gives me this matroid MF.
Good.
And if I can just go, if I look at the definition of the independent sets in MF, it tells me that a set is independent if only if all subsets satisfy the size of the subset is less than or equal to twice the number of vertices incident with J minus 3.
Okay.
And this is the same as the Polacek-Geringer theorem. So it tells us that a set is independent in the rigidity matroid. So Polacek-Geringer theorem tells us that a set is independent in the rigidity matroid if and only if it satisfies this condition. And this is the same condition that defines the independent sets in Edmonds' matroid. So it tells us that the two matroids are the same.
So the forcefulness on the next slide is simply that Edmonds also gives you the rank function.
Yes. So once we have the independence characterized by this simple submodular function, then Edmonds gives us the rank function for free.
Got it. Thank you. That was my question. Okay.
Okay.
Okay, so there's several more comments and questions, but I guess we can continue, and anyone who wants to have a break before the next talk can have their own break. So maybe we just continue. So Tibor says it may be interesting to note that you don't need Edmonds' theorem, that you can do a simple direct proof, just using Polacek-Geringer. Yes.
In fact, there's I think when we first got into so Tibor Jordan was the one that introduced me to rigidity theory, and one of the first things he showed me was a simple graph theoretic proof of Lovasz-Yemini. So yes, there is. We do not need to use the machinery from matroid theory, but I wanted to introduce this machinery so people were aware of it. but yes, it's nice to point out that we do not know it there, yeah.
Another question. So Will asks, which graphs are generically rigid for all D? So how common are graphs satisfying this condition?
Okay, sorry, Tony, can you still hear me?
Yes.
So for some reason, I stopped staring my slide. Oh, it's come back. I don't know what happened. Maybe I was fiddling about with the mouse. So sorry, what did Will ask, Dave?
We'll ask which graphs are generically rigid for all D, and how common are the other graphs satisfying this condition?
So you want a particular graph to be generically rigid for all D.
So I guess he's saying that simplexes are generically rigid, but which other graphs can be, and how common is it to be rigid?
Well, I don't think any other graph could be rigid for all D, because as soon as you have two non-adjacent vertices, if D is large enough, you can use the other vertices as a hinge, and you can flex the two non-adjacent vertices about the hinge.
Mm-hmm.
So complete graphs are the only graphs that are rigid for all D.
Alex asks, is there a characterization of the set of graphs from which all minimally rigid graphs can be obtained through 0 extensions and 1 extensions?
So I guess K3. So you have to allow K3, and you can obtain all minimally rigid graphs from K3. Presumably, we're talking about 2 dimensions, are we?
I guess so. It doesn't say in the question. Alex, do you want to comment? Yes, he was assuming D equals 2.
Yeah, so we have to include K3, or if you prefer, you could start off with K2. And then once you get K3, you get everything. And if you don't have K3, then you don't get everything. So a minimal set would be K3 or K2. And then if you wanted other sets, then you could do a 0 extension or a 1 extension of K3, and you would get bigger sets, but they're a bit redundant. Is that okay?
I was wondering if the question was sort of asking, so it's true that you can get all minimally rigid graphs from a minimally rigid subgraph of it. So starting the recursive construction from a rigid subgraph.
Oh, yeah.
So I wondered if that was what it was getting at, this question.
Yes, that's true. So if we're interested in constructing a particular minimally rigid graph, and we have a particular minimally rigid subgraph of that graph, then we can construct the larger graph from the smaller minimally rigid subgraph using 0 and 1 extensions.
And Bob asks, what happens if you take 3v minus 6 for graphs in free space? It does not correspond to rigidity, but does it correspond to anything? And I think Walter and Jim have sort of answered, and asking a new question. I'm guessing that Bob means, what do we get with 3/6 sparsity for sufficiently large vertex sets? Oh, and then Tibor's answered that. In some cases, 3/6 sparsity characterizes independence in free space, say for planar graphs or for squares of graphs. So I don't know if you want to add anything to that discussion.
Well, only that you have to be careful when you say 3/6 sparsity that you do not imply it for sets of size 2, because then nothing is independent. So it's 3/6 sparsity with the added condition that you only apply it to sets of size at least 3. Then you as you say, for planar graphs, it gives you a matroid, but you can't use Edmonds' theorem for this matroid because the only exclusion allowed by Edmonds' theorem is the empty set.